So let's see how some of these giant component conditions, and I'm writing this down in this way which isn't, which I sort of said isn't great from an understanding point of view, but at least in terms of these distributions, this is the right game. So we stated that as long as run along an edge, hit a node, as long as the number of other friends that these nodes have, right, random edge, hit a node, as long as that average number of other friends that node has is greater than 1, then there'll be a giant component, right? And you know, when we can put in things like disease spreading and so on, but this is just about the structure. And so we got to this, we derived this result, it's the second moment minus the first moment divided by this one. We talked about how you can mess around with this, but this is fine. And the things explode if you have high variances, right? Your friends are strange. Okay, so we're going to write this in terms of generating functions. And so we first need a generating function for this R sub k. And so this is a, this will be, right, so this will be the most important other one that we'll have. And I'll use this notation, right? So this is a generating function for the underlying degree distribution. This will be the generating function for this guy. There'll be two other related generating functions, and they will be for, given you hit a node, what's the probability that it is part of a component of a certain size, right? So that'll be a probability of a size. Size, of course, is an integer, right? It's like 1, 2, 3, 4 nodes. And given you hit a node, what's the probability that it leads to a component of however many nodes as well, right? So they'll be, these are obviously local things. These will be non-local distributions. Anyway, these things will all connect together. But this is all we need. There'll be these sort of 4 generating functions that matter. Okay. So it turns out the giant component, right, is we wanted the average number of other friends. And so we know how averages work for generating functions. It's just the derivative of the generating function evaluated at 1. So from a, you know, in the notation of generating functions, so we're abstracting, this will be our condition. The first derivative evaluated at 1 is greater than 1. Okay. Okay, how are we doing? There's a few more slides here. Okay. Okay, so let's connect these two generating functions. Everything ultimately has to come, because we're just talking about random networks with arbitrary degree distributions, everything's just, and everything's wired up randomly. There's really only one thing about these, and that's P sub k, right? The distribution of degree. Yeah? Should we move on? Yes. Okay. Always the same thing, right? We want a generating function for a distribution. We just take whatever it is, we slap an x to the power of k on it, and sum over k from 0 to infinity, because we're kind of in that game. It's always going to be 0 to infinity for us. Can be more general. This is R sub k, right? So it is the probability that you, because we're talking about having k other friends, it's probably that you hit a node that has k plus 1 friends, because the plus 1 is the edge you're coming in on. So there are k plus 1 ways to get to nodes of degree k plus 1, and the normalization is on the bottom there is the average degree. Right. Okay? So that looks pretty good. It looks a lot like the, it looks very close to the generating function for the underlying degree distribution, except there's this piece out here, right? There's a k. So that's a piece we have to modify slightly. Okay, we're going to shift the index. We'll go from k, j equals k plus, k to j equals k plus 1. And that average degree on the bottom can be pulled out. So let's see what we've done, right? So the average degree is going to come out here. We're going to shift indices. So k plus 1 is j. There's a k plus 1, that's j. And then there's x to the k, and that's going to be j minus 1. And if k starts at 0 and goes to infinity, then j starts at 1 and goes to infinity. So we've cleaned up our some limits. Okay, yes? Excitement? No excitement. All right, it's pretty good. Sums are really very nice. Okay, so we've sort of started to see this a bit, I think. So every time we have something like this, a j, x to the j, whatever it is, we can usually mess around with a little bit. Maybe we have to put in an x or take out an x or something. But this piece here is just staring at us as derivative. Jx to the j minus 1. So we avail ourselves of that situation. You know, the pj just sitting there, the pj's. Wow, I could really use that. And then x to the j. Seriously, I mean, there's a whole world of bad puns just sitting right there, yeah. So wrong. Okay. Anyone ever listen to Bugle? Bugle podcast? Okay. It's, so John Oliver, he's on HBO, Englishman? Yeah, so he used to do this with this guy Andy Zaltzman. Anyway, it still runs, but Zaltzman's in charge. And the puns, wow. Pun runs, he goes on pun runs, quite aggressive. Okay, so we're going to pull the d by dx out. Nothing could go wrong, right? That's just like math, right? No one ever should worry about these things. But it's true, like horrible things can happen when you do this sometimes. But physics, yay, right? What's pretty weird about generating functions, it doesn't even matter if this thing converges, right? You just we just made it up, it's okay. It's just a function. We're just going to stick things next to x to the j and just sum over them and everything's great. Okay, so, all right, but the point of so what we've done, we've slept this thing out, which is the technical term there, we've slept it out, and now we have what is an underlying feature for our network. We're back to a generating function for p, right? So so the game is to try and express everything and the stuff that comes later in terms of the underlying degree distribution generating function. So this is almost the generating function, but it is we're missing the first one, right? And the first one is p0 x to the 0, right? Which is p0 times 1. So we can say it's the generating function for p minus the first term. We're like, yes. Derivative, that's still hanging around, right? So it's a derivative of a constant. So this will go away anyway. So that horrible little, unpleasantness, just lacks aesthetic appeal, goes away, and we end up with a much nicer story, okay? Truth and beauty are not really actually connected at all, but we try to make that happen. So this will be beautiful but obfuscating, I think, is what happens with generating functions. No, it's powerful, but yeah. Anyway, so it's just the first derivative of it. So the average degree in terms of the underlying, this generating function is, for those of you who've been watching, it's hard, right? How do we express that in terms of the generating function for p? Derivative of 1, right? So this is looking kind of nice, right? This is actually, right, the average degree, and this is with, it's not set here, but it's with respect to the p distribution, the degree distribution, is this blob, evaluate 1, and it's the first derivative, yeah. So that's kind of nice. It doesn't do that, right? Oh yeah, I guess you can see a little bit, okay. So that's true, and then, so this is very nice, right? So this is the generating function for the R distribution, which is this useful one, right? It's the one that if you follow a random edge, hit a node, what's the probability that it has k other friends? It has this quite elegant structure. So we've just found the generating function, right? We had a condition for a giant component, which is really what's the average of this distribution. So again, that's the first derivative of this, evaluate at 1. So we'll do that in the next slide. But if you look at this, there's one basic thing that we need, which is if you set this equal to 1, then this has to sum to 1, right? This is because this is a distribution. R is a probability distribution. So whenever we have a generating function, we set x equal to 1. Again, there are some exceptions, but set x equal to 1, we should have 1. And that's indeed the case, right? So this is 1, blob over blob. So that's nice. Good. So it looks healthy. But you know, you kind of have to get to this piece, right? I mean, this is not obvious, right? It's not immediately obvious. You start to see derivatives kind of give you this rich gets richer thing, right? This k. So they give you that boost, right? So it sort of makes sense. The derivative. So derivatives in generating function space, you know, go back to a k or a k minus 1, right? A linear factor in probability space. Anyway, lovely thing. Yeah, t-shirt. Okay. Maybe a hat. Sorry. Make generating functions. I shouldn't do that. Okay, so our contagion condition is this, right? First derivative of the R's generating function evaluated at 1. That has to be greater than 1. By the way, I just want to say that I've really tried in all of these notes to kind of unify a notation. If you go to, I mean, as you should, I suppose, but if you go to papers, you'll see all sorts of crazy things, right? So there'll be f for the generating function for p, there'll be g for the generating function for the other one, there'll be an h for someone else, and there'll be f naughts and g naughts and h, all sorts of stuff. So it can be quite confusing. But I've tried to call all generating functions f and then put a subscript for which thing it is, right? Because we really quickly run out of stuff, right? IJK is great, but then L is a bit of a sketchy one, and then M and N are for another team. You know, L's can look like I's and ones and stuff. We have a lot of triples, right? That are kind of coherent, and then the next one is part of a different team. Okay, good. All right, so we have this, so it's a simple thing, right? We're just going to differentiate this. This is a constant on the bottom. The derivative of this is just the second derivative. So that's a nice thing as well, and then we're going to set it to 1. So this is the first derivative of the generating function for R, you know, just carrying on. So it's going to have a second derivative of the p piece up there. And again, this is going to give us the k minus 1, right? When we differentiate a generating function, a k will come down internally, and then a k minus 1 will come down. And that's our condition, right? We wanted actually that average of k times k minus 1. And that's what it is, right? So this all amounts to, yeah. That first thing, you can kind of look at that and see and think, oh, that's k minus 1 average with respect to this p distribution. The bottom one is just the average of k. Right? It's a generating function, second derivative. So derivatives give you a k, and then another one will give you a k minus 1. Because we haven't, it's not xd by dx, right? We haven't shifted it back up or anything. And then first derivative here. Do you want me to write that out a little more? I feel like I should. Interest of lying less. So yeah, so we've got f. I can lie more if you want. If that would be better. So this we've just decided, claimed, actually derived, it's true, it's really true. F of p of 1 and f of p. So everything ultimately is going to be in terms of just the generating function for p. Bless you. And you know, I know we've done it, I just want to do it again, I guess. Iteration is good. So, first derivative. Right? I mean, I'm saying these things, but I might as well put them down. It gives us a k. Look at that. Look at that madness. K, p sub k, x to the k. And then minus 1. And then we've got an fp double prime of x. Differentiate again. Not going to worry that. And then the k minus 1 comes down. P of k, x to the k minus 2. Right? So we've got the average of this guy. So if we set If we set x equals to 1, in this case, then of course we just get the sum of these and we get 1. If we set x equals to 1, we get the mean of k, right? So x equals 1 gives us the mean of the mean degree, and x equals 1 here, setting x equal to 1, we get the mean of k minus 1. I guess what I'm trying to say is you can kind of eventually look at these things and see that that's what's going on. Right? Derivatives translate to linear pieces. How are we emotionally about this? Actually, you don't have to answer that. Sorry.
Does the fact that the F is capital mean something? Or is it just like a notation?
Yeah, no, that was just to make it take up space. Authority. That's right, yeah. Yeah, we tend to do that a little bit with, I guess, Fourier transforms. Often it's a little f and then a big F. You know, people do that a little bit. Yeah, but yeah, you can get yourself into trouble by going for a little lowercase stuff, and then you put some subscripts, and so it just doesn't have the weight to hold on. So, yeah, it was all about heft. Yeah. It's true in this case, we do use capital P for P sub k and r. Again, really, you'll see it often it's like little p's and so on, but it's just like a small r, that doesn't, yeah, again, yeah, it's just weak. Okay. But ultimately, yeah, it's there because I thought that was a good idea, so.